Alright, so now we're back with differential equations. This is going to be part 2, where we discuss solving them. The first video on this was about the basics and modeling, so make sure you've seen that or you know the concepts. And we shall get into it right now. So, whoops, I forgot to change this. Currently we're in this video. So, in this video we're going to go through the basic derivation of Eulers Method, and then its extension, which is Runge-Kutta, more specifically the 4th and 5th order, as this is a built-in function in MATLAB and it's very popular. Then we're going to take the spring mass damper system that we derived in the last video, and we're going to apply that in MATLAB using both of these methods and see how the solution looks. Finally, originally I was going to do the Lorentz system example where you apply the Lorentz system dynamics, but while I was researching the topic, I actually found another video which is exactly this topic, and it's by a professor who goes to University of Washington, I believe. I will link that video in the description. I highly recommend it. It covers everything I do, but better. So, with that being said, let's start with the derivation of Eulers method. So, start drawing. So, the derivation is pretty straightforward. Initially, we had this formula from our simplification. This is from reduction of order. This is the general form that we have. And a way that we can look at it is the slope of the slope is equal to the function that we get from the reduction of order. And if we apply this to a line, or more specifically the equation of a line, here's what we have. Well, let's see, the equation of a line is this, slope times x minus x naught. And, we can shift it around and we get y is equal to y naught plus m times x minus x naught. Well, m is the slope, and this derivative term is quite literally that. The derivative is quite literally is slope, if you wish to see it as such. So if we apply this formula here, we can see that y is equal to y naught plus f of x minus t, this is the m part, and multiply this by x minus x naught. And this is a pretty expected, this is an expected result, right? If we have a function and we know, we have some point x and we have some point t and it produces some output x. If we know the slope is, say, this number, then from it we can extrapolate and say, hey, this is where our next point is expected to lie. Now, obviously, assuming that f is a continuous and smooth function, maybe it doesn't follow exactly, a linear path. Maybe it does something like this. In which case we have, it's a little bit of error that's happening. But for our purposes, we can assume that this error is negligible or it's within whatever tolerance we set. And furthermore, this would be the point t plus, this would be t plus your small time step, so delta t here. And for Euler's method, we assume that this time step right here is constant. We just assume it's delta t, and the next time step will be another delta t, and so on and so forth. So if we were to change the equation we had for a line, so this is a general line. This is unrelated to this at the moment. But if we were to combine it all, you might see that I have a bit of terminology issues. But if we were to apply this here, what we would get is that the next step of our function is the previous step plus the slope of that step times the distance in between. Sorry, this would not be x, this would actually be t plus delta t minus t. And as you can, sorry, that's very weird, minus t. And as you can see, the t's here would cancel and we're just left with the delta t. So, and we have a term for that, we just call it h, or the delta step. But this can be further simplified into h times f of xt, where we defined h as delta t from here. Okay? So, this is pretty straightforward, right? We know what this is. This is the equation of a line. We're computing the next step based on the slope and time step that we are taking. And this right here, this equation down here, this is quite literally Euler's method. And we can apply it however we see fit. As you might expect, there are times when Euler's method may not be accurate enough, right? As you can see here, there's quite a bit, if our function is too sharp, there is actually quite a bit of error that builds up. And for that, there are other methods that we would use. We would have to, either decrease the time step until our error is within bound, or we would have to use other schemes. One very popular one is called Runge-Kutta. When I highly recommend you, Google this if you're actually interested. But using the same definitions as before, it defines. So this is our Euler's method. Runge-Kutta is defined as such, and there's no way I can remember this off the top of my head. And once again, this is not my field of interest, per se. But I think it would be a bit of an injustice if I didn't mention it. So, yeah. So this is the formula for Runge-Kutta, and then each of these coefficients is actually f of xn comma tn. A2 is equal to h times f of xn plus h over 2 y, not y, sorry. So I'm copying this off the internet, and it is not doing me much justice. Okay, 1 over 2. A3 is equal to h f of xn plus 2 over 2, comma, y of n plus k over 2, and k4, which is equal to h f of xn plus h tn plus k3. And as you can see, there's a lot of stuff going on here, and rightfully so. The expression is quite long, and there is a lot of computation that's going on. However, the result is that our formula is a lot more accurate. And if we were, let me see if I can quickly find a graph. Okay, I think this graph might be a little small, but let me see if I can drag it over and extend it a little. Whoops. Come on, zoom in. There we go. And so what the formula does is it accounts for the derivative at a certain point, yes, but it also accounts for 3 extra terms, which is the derivative at the point of interest, as well as the 2 intermediate derivatives. And from this, it computes the next time step. And as you can see, accounting for the steps in between, it allows you to have much more precision than simply accounting for the beginning step, as Euler's formula does. And so this formula is very useful, and I don't know if I mentioned this already, but in MATLAB there's a function called ODE45, which quite literally, it's just this method, but optimized for, and it's used for MATLAB. So now that we've gone through this derivation, we won't necessarily be using this. However, it is definitely an exercise to code it in yourself. We will primarily be using Euler's method and ODE45 to solve our equations. Oh, that tab died. So, let's get right to it then. I'll move this off screen, open MATLAB, and using the information from the previous video, we will solve the spring mass dampener system. So, let's get right to it. In case you're wondering, this notes is the code that I know works. Unfortunately, I'm not capable of writing code that works on the first try. Oops, start. And yeah, that's why I have to keep it open. But nonetheless, I know it works. That makes me feel better. Much more confident. Otherwise, this video would take forever. So first we have our parameters, and we're going to have to define our constants, right? Now, obviously we can just define our mass. We're going to define it as 1 kilogram. Our spring constant, we're going to define it as 4. And our damping coefficient, for now we're going to keep it as 0, and you'll see why later. Which is, if you were to actually solve the differential equation, when you don't have any damping, you would expect a pure sinusoidal wave. And so this will be our test, you could say, to make sure it's, our functions and our script is working as expected. So then we have our initial conditions, which we're going to define as our x naught vector. And we're going to say that this is going to have, the first index is going to be our position. So we're going to say that it starts at 1. So this is initial position. And we'll say it starts with no velocity. This is our initial velocity. If you're a little weirded out by why it's x, 1, and why we have our position and velocity vector right next to each other, if you remember from the previous video, we defined a vector such that we had x1, which was our representation of x, and we had x2, which represented x dot. So this is exactly what it's doing, right? We have this is our position, which is x, initial position, and we have x dot, which is our velocity. And this is how we're going to be formulating our solution. So we've set up the initial value. Now we just need to set up the solution parameters. So let's just set up a solution. So obviously we have to have a start time. We'll start at 0, and we have a t stop, which we'll set to say 10. That should be sufficiently long. And we'll have a time step, which is our delta x. Now, obviously we can choose to make it however big or small you want, but for most cases, smaller is better in that it's a finer step. However, you don't want to get too small, otherwise the computer won't be able to accurately represent your data, and other errors will start coming in. That's a topic you will learn in numerical analysis, for those of you who are interested in learning it. Personally, I've simply done the bare minimum of research. But yeah. So after we have our time start, stop, and we can define our time span, which is going to be t start, t, and t stop. So this will go through 0 and 10 at this increment, as we would expect it. It'll have like 10,001 values. So this is our time vector. This will be plotted as our x-axis, you could say. It's our independent variable. Then we have to set up the matrix for our solution. So we're going to call x1. This, you'll see why I'm calling it x1, but we're going to define an empty matrix, and it's going to be the same length as the t-span vector. And this is important as we don't want any discrepancies. We don't want one vector to be larger than the other. And since we're here, we can define the first column of our matrix as the initial conditions, right? So we'll have a massive matrix, a value for position and velocity, and the initial value will be our initial values. Pretty straightforward. From here, we can look into solving our problem. So this is going to be a numerical solution. MATLAB is capable of doing symbolic math, and it is possible to solve this thing, the way you'd solve it on paper. But we're going to, for the appropriate reasons, we're going to assume that we can't do that for every equation. So first we have our Eulers method. Actually, before we begin our solution, we actually need to set up our system, which we'll do that right now. We'll create a new script, and we'll call this the spring mass dampener equations of motion. And this will be a function, right? So if you remember from the last video, we defined our output as dx, and we had some function, which is in this case the equations of motion, of time, position, or current state, and then we had some of our parameters, which would be mass, the damping, and the spring constant. And I'll give myself a bit of room and end it. So these are derived in the previous video, so I'll just leave a comment. Derived in previous video. And remember, the format of this is very tailored to our application, right? So we have our first variable, the first index of our matrix is going to be x, or position, as you could say. We have our second value, which is going to be x dot. This is our velocity, and we don't want to lose track of this. Finally, we have mass, we have our mass, we have our damping, and we have our spring constant. Whoops, there we go. Now let's fix this while I'm here. Ah, come on. There we go. All right. Now, if you remember from our previous video, the way we derived this, let me pull it up here. So this is from the previous video. We have our derivative terms. So the first derivative is equal to x2. The derivative of our first term is equal to the second term. The derivative of the second term is equal to this mess. For now, we're assuming that this f of t is 0, but it's very easy to implement this. We would simply add a force up here and modify it as needed, right? It would depend on time, and I will explore that in a future video, actually. So anyway, we can get into the derivations. Someone sent me a message, and it's irrelevant to the topic, so we will put it aside. So we will set up our matrix. So we want it to be a column matrix, so a 2 by 1, and we'll set the value of each one. So the first value is the second value. So the derivative of the position is velocity, and that's what this first term is. And our second one is negative b times x2 plus k times x1. All of this will be divided by the mass. And if you're confused about where any of these came from, I highly recommend checking the previous video, drawing the free body diagram, doing the analysis, and deriving the equations yourself, and then performing the reduction of order. But for now, we have our system set up, so this will return. As you can see, that gives you a little bit of an error here. It says t might be unused. So this comes in handy later because the ODE solver that we use, ODE 45, asks that t is the first variable, and it's a bit selfish and a bit picky about it, so we have to include it. This error means nothing here. I guess if we were to add a time-dependent force here, so let's say we would have some function here that our force, it depends on t, and it would be some expression, right? Let's say it's, I don't know, it's a step function, whatever it is. But here, if we had this here, then it would be some function of t. But in any sense, we don't have that here, so it doesn't matter. But that's where the t term would be helpful. You can suppress this if you want. You can leave it on if you want. I personally am not bothered by the yellow highlight and red underline, but if you are, definitely suppress it. Anyway, so we've defined our equations of motion. Now we just need to solve them. So solving them is not very difficult, right? So in Eulers Method, let me pull up the thing. Okay, so here we have our Eulers Method. As you can see, it uses an index of n plus 1. Now, for us, this could very well be time, right? We can define something that starts at t0, right? We can define n as to be equal to t, and we can say that the initial position, the position, and the next position, they depend on each other through this relationship, and we can just say n is equal to t, right? It's a simple substitution, and you can reason through it yourself why it's appropriate to do such a thing. Keep in mind, we aren't starting at 1, actually. We're starting at 2. The initial position, which is x0, is already set for us, right? The first value is already set for us. We need to start at the second position with the formula and proceed from there. And we'll be going through the length of t-span. There we go. And end. Now, here we have to ask, how do we actually convert the formula that we have into a form that how do we convert the formula that we derived into a formula that is usable and codable in MATLAB? So if you remember correctly, what we had was we had to put in the next step. So the next step would be I. Actually, you know what? Let me go back to the whiteboard and just clarify something, because I don't want to make any rash decisions. So this is the formula that we had. Now, if we were to take this out and change it a little bit. So instead of using n plus 1 and n, we'll convert this into n and n minus 1. Right? So instead of relating the future step to the past step, we're relating the current step to the past step. And this sort of changes, you can reason through why it would make sense, right? It's the same thing, it's just we're looking at it from a different perspective. And so what we can do is we can rewrite it as x of n is equal to xn minus 1 plus h times f of x n minus 1 t. Sorry, there should be an n here. I may have neglected that. And so this is the formula that we would be using when we try to implement it into MATLAB. X of n is equal to xn minus 1 plus the step times the function at the previous step. So let's implement that. So we have x of I, or sorry, no, we have to look at all the rows and the column I, right? That's the way we have defined it. And we are going to set that equal to the, whoops, wait, let me do this, x1, right? Our solution is x1. And so we look at the previous step, which would be all the rows and the previous column, right? The previous data that we have. And we're going to add that to the time step that we took, delta t, multiplied by the function, which for our case is the spring mass dampener equations of motion. And in here, if we can just copy paste directly what our inputs and outputs are. And we see that we have to put in a t, an x, an m, and a b, and a k. Well, this x is supposed to be the previous, or sorry, the state before the one we're computing. So in our case, this would be x of, so this would be x1, and it would be all the rows, and it would be at the previous step, which is I minus 1. And our t variable, well, that's just our time steps. And quite honestly, it doesn't matter what we put in here, but we can just throw in I. In a more realistic situation, what you would actually want to do here is you would put t span I minus 1. But just to save a little bit of processing power, and because we know that it's useless, we can just put in 0 for now, right? It makes no difference. And then we have our mass, damping, and spring constant. Pretty straightforward stuff. And this is our Eulers method. This will iterate through everything, going at this time step, starting at this time, ending at this time, and it will solve the equation for us. Let's add a little bit of space. So now we have our solution. So let's do this. Let's visualize it. So visualization, most important part of getting data. We'll create a figure, and we'll plot the time data on our x-axis, as is the independent variable, and we'll plot the solution on the y-axis, which is our position. And so once again, recall that only our first index is position. The second one is velocity. So we only really need to plot the position. And so to plot the position, we simply say, okay, look at the entire first column, and look at the first row of every column. And that is what it will plot. We're not doing any fancy color stuff today, just because this video is going to be quite long. But if we run this system, as you can see, there's a lot of trial and error I went through to figure out which things work and which things don't. Oh, we already have an error. In line 1. Oh, start display. Whoops. Yeah, as you can see, I'm very prone to errors. Okay, well, this is a bit weird. We have data that doesn't necessarily make sense to us. And let's try and figure out why, actually. Okay, so the error. Found it pretty quickly, actually, which is in this line. Bit of a typo. This is supposed to be x1, right? We want to set our initial conditions into the appropriate matrix. And this was pretty straightforward, but now if we compute it, we can see that we have a sine wave, right? So this follows pretty straightforward, right? If we have no damping and we have a spring on a mass, it will follow a perfect sinusoid as it oscillates back and forth. And if we check, we can even see that we have a period of pi, which, to be expected, right? we have a mass 1 and spring constant 4. But now, if we add a bit of dampening, say by changing this to 0.4, well, now we would expect some sort of decay to occur. And if we plot this, we see, yeah, that decay is clearly present, right? On each loop, it's losing some amount of energy. And the faster it's going, the more energy it's losing, right? So this specific, so to go from here to here has a bigger difference than going from here to here, because while the spring is moving here, it's got a much greater velocity than down here. So this is solving it with the Eulers method, and now we will quickly solve it with the OD45 method. And keep in mind, this is built in, so anyone with MATLAB has access to this. Now, to solve the OD45 method, first of all, I would highly recommend you look at the help pages. So once again, help OD45. This will take a bit of time to load, and it gives you some other solvers depending on what you have. But you can see that there's a lot of documentation, but this is our general format right here, right? We have our time out, we have our solution out. It's equal to OD45, put in the function, put in the time span, put in the initial conditions. And you know what? That's exactly what we'll do. So we have our time vector, which is going to be t, our second solution, which is x2. This is why we renamed it as we did. Put in OD45, put in the function, so at t comma x, these are our solutions. Spring mass dampener, equations of motion, putting in time, position, mass, damping, and constant. And then we have to put in our t span and our x naught. And OD45 should solve that pretty nicely. Let's just do this. Let's create another figure. On this one, we'll plot the time and x2. Once again, we're only going to be plotting the first. So OD45 is a bit weird, so we did everything in columns, and OD45 did it all in rows. It makes no difference, really. It's just a matter of, what you end up doing. There's probably a better way to do this, but I'm a student, so I don't care. I do whatever feels right to me. Anyway, now that we have our solution set up, we can just go to spring mass dampener, and we can see that we have multiple figures created here. So, whoops, I forgot to delete the first figure. This is what we had originally. But as you can see, they're literally the same, right? There's very little error going on between them. And, if you feel like you want to check how much error is between them, you would simply subtract one solution from the other and plot that on a graph, and you would see visually the error would likely, decay over time. And if you want to compare this to the, the exact solution, you could solve the equation on paper, get the function that represents the behavior over some period of time, plot that directly, and compare all three graphs. Anyway, this has been the video on differential equations. As you can see, we have the results that we wanted. We are now able to solve differential equations quite easily, right? A bit of setup, obviously, and little painstaking efforts to get used to. But now we can define any arbitrary function, any arbitrary system, and we can solve it. So with that being said, that is the end of this topic. People definitely really want my attention right now. Yes, as for the Lorentz system, so this is something I was going to show. Whoops, I'm not going to open that here. There might be a bit of suspicious material, but here's the video I found, and I was going through it just to make sure. He uses a very similar method to solve the equation, and I highly recommend this channel. Very useful stuff if you're interested in dynamical systems and the related content. Yeah. Also, I believe his code is much easier to read and much easier on the eyes than mine. But yes, that is all for this video, and that is all. Alright, have a nice day, you guys.